the acid and base chapter. And remember that basically an acid is something that's able to produce H plus ions in solution. H plus ions, H3O plus ions are essentially the same thing in acid-base chemistry. So when we have H plus or H3O plus, it's really representing obviously the acid part of the solution. They're used interchangeable in both sort of formulas, also equations and reactions. A lot of times, I will sort of probably use H plus most of the time, but almost in every instance, if I should write H plus, you could pretty much replace it with H3O plus. The real difference is, as we sort of saw last time, that if you write sort of a reaction for, say, an acid that's, sort of dissociating in water, if you do sort of include the water in the reaction, that's how you'll get the H3O plus. So, if we looked at like hydrochloric acid, and you could definitely, you put water in there just to show that it's breaking apart, and you will make H3O plus and some Cl minus. You could also show this acid as well doing a similar type of dissociation, and it could be represented without the water in the equation. And again, here you'll get the H plus rather than the H3O plus. So again, this guy and this guy, basically the same thing, is whether or not, and a lot of times the case of an acid, you want to kind of include the water or not, and it's perfectly fine to do it either way in the case of an acid. Most of the times when we write sort of reactions for bases, it's a really good idea to include water in the reaction, because a lot of times people struggle with sort of what's reacting, how to get that equation to be written. So really, what is sort of an acid or a base? Well, it is, sort of this guy here. It's an acid is really something that's able to produce H plus or H3O plus in solution. And when we talk about that, we're talking about sort of free H plus or H3O plus, not combined with anything else, basically free floating in the solution. And that's really what, sort of an acid is able to do. A base, on the other hand, is able to produce free OH minus in solution. And again, the production of that OH minus is really what makes something sort of a base. And we also talked about sort of a more general definition of acid and bases, and one oftentimes that people sort of use when describing acid and bases, and that's what's known as the Bronsted-Lowry definition. And the Bronsted-Lowry definition is an acid is a proton donor. So in the Bronsted-Lowry definition, an acid is a proton donor, which basically means it gives away an H. And as we talked about last time, it's not just the H, but it is also the plus part of it, which is really important in terms of charges and stuff like that. While a base for a Bronsted-Lowry is basically a proton acceptor, so it accepts the proton. Sort of a consequence of the Bronsted-Lowry definition is when we have an acid and a base sort of donating and accepting an H plus, what they create on the other side are partners that are related to each other. And these partners are related to each other by one important sort of bond that ties them together. And it is this right here. It is one H plus and only one H plus difference. And that's what brings up our conjugate acids and our conjugate bases that are produced. So in the case here, when we actually can, if we look at, for example, hydrochloric acid sort of breaking apart, when we look at this, what's really happening is the hydrochloric acid is acting as an acid, which is good. It is donating its H plus basically over, and that makes our hydrochloric acid, obviously the acid. When it does so, it basically makes a partner on the other side, which is known as the conjugate base. So this would be the acid. This guy here would be the conjugate base. And we see a similar relationship between water, which basically accepted the proton, and H3O plus there. So these two guys here are related to each other as well. And again, because the water basically accepted the proton, it's acting as the base, while the H3O plus is acting as what is known as the conjugate acid. So as we also talked about last time, acid and bases just sort of like, you know, this is an acid, this is a base, typically found on the left-hand side of the arrow. Are your kind of conjugate pairs are found on the right-hand side of the arrow. And again, the only difference between those two is 1H plus, and can only be really 1H plus difference between those two guys. If it's more than 1H plus, then they are not technically pairs. And we talked about that, I think, at the very end last time. And the reason for that is when something, for example, like sulfuric acid, when it loses an H plus, an acid, and it has more than one H plus to give, which makes it like a diprotic acid. Monoprotic means it's got one H plus. Diprotic means it has two H pluses. But when it has more than one H plus, they actually do come off one at a time in sort of a stepwise fashion. And that's why when we talk about pairs, it is only that one H plus difference. So for example, I think number 2 there that we crossed out was H2SO4 and SO4 2 minus. They're definitely related to each other, but they are not related to each other as an acid conjugate base pair. And that's because, again, the difference there is basically 2 down the road from each other. And as I sort of demonstrated, I think at the end last time, you know, H2SO4, its partner really would be HSO4 minus, and SO4 2 minus's partner would actually be HSO4 minus as well. But going directly from the H2SO4 to the SO4 2 minus is really 2 H pluses of difference. So it is not a pair between those two. Any questions on that stuff we talked about last time in terms of acids? Okay, so I think we did this example here. So why don't we look at the next example here? Why don't you give it a try here? Take a couple minutes here, and or a minute or so. And what we're looking for is what is the formula of the conjugate acid of this base. So take a moment or two and see what you come up with. A couple of things. So we're looking for the formula of the conjugate acid. Now, they're nice enough to tell you that these are bases, and they may not tell you that. So you always want to kind of maybe think about these things sort of backwards. So if you remember sort of the general setup, acid plus base basically makes a conjugate acid plus a conjugate base. And again, if you have sort of an acid on one side, his partner on the other side would be the conjugate base. Conjugate acids partner would be the base. So in a problem, if they, you know, for example, just ask you what's the conjugate acid, you could think backwards and go, okay, these guys are bases. Hopefully the one thing that you do know for sure is it's an H plus difference. And really the key that a lot of people have struggled with is, you know, should you put it on or should you take it off? So if you sort of think about this backwards and you understand that these are bases, the definition of a base is something that will accept an H plus, and that means that we need to actually put it on in this case. So we have C6H5NH2 to begin with, plus an extra H makes it a 3, not just an H, but also a plus makes it a plus. So this would be the correct answer. Looks like number 2 there is a winner. So sometimes it's very helpful to sort of think backwards about it, and especially when you're a problem and you're like, hey, given, you know, what is the conjugate acid or what's the conjugate base, you could kind of think backwards and determine, are you looking at an acid, which means obviously you should take away the H plus. Are you looking at a base, you should add the H plus. So sometimes that's helpful to kind of look back in that direction. Any questions on that particular one there? So why don't you try one more here? Let's say we had HCO3 minus, and why don't you write the conjugate acid for it? Why don't you also write the conjugate base for it? So take a moment and come up with the formula for both of those guys here. Okay, so let's take a look at this one. So same approach. We'll start with the conjugate acid. So again, if you're just given the conjugate acid, you could kind of remember this relationship we just talked about. Again, really what that means is in this particular case, the HCO3 minus would be acting as a base, which means it will actually accept the H plus, which means it should be 1H plus more, which would be H2CO3. Any questions on that one? Now, if we're looking for the conjugate base in this case, that means that we are starting with it as an acid, which means it's actually going to donate an H plus, which means we're going to subtract an H plus, and we will end up with CO3 2 minus. Again, you could see in this case, these two guys are not partners because there's too many H pluses. It's actually this guy and this guy that would be partners. This guy and this guy would be partners as well. Questions on that there? You may also notice from this that in one case, this acted as an acid, and in the other case, it acted as a base. And there are a lot of things that can do that. And a lot of times this happens when you have something that has an H and something that has a minus. And it allows it the ability actually to do both things. It can act as an acid or a base, depending on the situation. And those things that have the ability to act as an acid or base are what are referred to as being amphoteric. So an amphoteric substance is a substance that basically can act, can act as an acid or a base in certain situations. And we'll talk about later on as well, you know, what, how you could determine sort of which way it would react. There's actually some things you could look at to maybe help you make that decision. But there are definitely things that can pretty much do that, act either as an acid or a base. Any questions on that or acid conjugate base pairs? So speaking of things that can sort of act as an acid or base, water is one of those things. Water actually has the ability to act as sort of an acid or a base. And that brings up an interesting property of water, which is sometimes referred to as the autoionization of water. And basically in this situation here, my arrow's a little off there. Sorry about that. Let me just go this way with it. I'll rewrite it this way. Basically, in this case, we have one water plus another water. And it is going to make H3O plus and OH minus. And one of these waters will act as the acid. Another one will act as the base. And this will be our conjugate acid. And this would be our conjugate base in this particular case. So water, and this is sort of what's happening with water all the time. They're kind of constantly reacting with each other. And again, one acting as the acid, one acting as the base. So this guy going to be kind of donating the H plus, this one going to be accepting the H plus. And we get this sort of reaction that occurs here. This is again what is sometimes referred to as the autoionization of water. This is really why when we think about sort of water or a solution, you know, these two guys in there is basically what determines whether or not this solution will be acidic, basic, or neutral. You might also notice that this water reaction has arrows heading in both directions, which would imply that it's a reversible reaction like we have up here. And in a reversible reaction, as we talked about in the previous chapter, that will set up an equilibrium. And water does set up an equilibrium. And an important equilibrium in terms of acid and bases and calculations, it will set up products over reactants. But just like we talked about when we talked about equilibrium, the one thing that we don't include in equilibrium are things that are liquids. So they remain relatively constant. So this gives us a relationship which is referred to as Kw. And Kw is the H plus concentration times the OH minus concentration. And that actually equals, as it will show on the bottom of the page there, 1 times 10 to the minus 14 at 25 degrees Celsius. And that's probably most of the time what you would be doing it at. This equation is, again, one of the first ones as well that, you will see as H3O plus and OH minus is equal to 1 times 10 to the minus 14. So again, as we talked about earlier, you could either use H3O plus if you like, you could use H plus. It is the same thing in this case. Kw is an important relationship because really it actually allows us to figure out whether or not the solution is going to be acidic, basic, or neutral. How does it do that? Well, we compare the H plus concentration, which is essentially the acid part of the solution, to the OH minus concentration, which is essentially the base part of the solution. And basically we could determine sort of which one is larger and which one is smaller, and it will help us decide, is that solution going to be acidic, basic, or neutral? So if we calculate the H plus concentration and it actually equals the OH minus concentration, by the way, that means they both will equal 1 times 10 to the minus 7 molar in that particular case, you will have a neutral solution. If you calculate the H plus concentration and it's larger than the OH minus concentration, basically the acid part is larger than the base part, it will be acidic. If you calculate the H plus concentration, it's less than the OH minus concentration. So basically our base part is larger than our acid part, it will be basic. How do you do that calculation? Well, the good news is it's pretty much the same calculation no matter which one you're solving for. You take, for example, the H plus concentration is equal to 1 times 10 to the minus 14 divided by the OH minus concentration, or the OH minus concentration is 1 times 10 to the minus 14 divided by the H plus concentration. Any questions on that? Now, it's also important to remember, and again, like I said before, for the most part, you will always use probably 1 times 10 to the minus 14. And again, even if they don't give you the temperature in a problem, you could probably safely assume that it is 25 degrees Celsius. One side note to that is it is an equilibrium constant value. And as we talked about in the previous chapter, equilibrium constants do change with temperature, which means if you do come across a problem where they tell you that the temperature is not 25 degrees, but maybe, hey, it's 30 degrees or 40 degrees or something like that. Technically speaking, you would need to find the Kw value at 30 degrees, 40 degrees, whatever it may be. My guess is usually in a problem like that, they would probably provide that for you in a textbook type problem or something like that. But is a good note to remember that, even though we kind of use this almost as a constant value, 1 times 10 to the minus 14 in almost 99.9% of the applications of using Kw, it still is an equilibrium constant value. So technically speaking, if you come across a problem, they specifically say, it's at a different temperature, then you want to make sure that you are using the right Kw value. Any questions on that? And again, probably a very rare instance where you would come across a problem like that, but again, it can still happen. One other also important note, especially as we're getting into these calculations here, you want to definitely make sure when you're putting these things in your calculator, make sure you are using your exponent button. So if you're still doing some weird multiplication, shift log type situation to try to put things in scientific notation in your calculator, you're going to find yourself off in a lot of these calculations. So make sure when you punch something in, you use that exponent button like we talked about, I think, earlier on here in the semester. The way you'll probably really recognize that you're having that issue is like we talked about earlier, you'll get kind of the front part of the number good. but the exponent part will definitely be off and stuff like that. So make sure, again, you use your exponent buttons. So why don't we give it a go here and try one. We want to know what is the concentration of OH minus in an HCl solution who has a concentration of 1.3 molar. And while we're at it, we also decide, is it acidic, basic, or neutral? So take a moment or two here and see what you come up with. Let's take a look at this. So we're definitely given the H plus concentration. So we're going to use our KW, which again is our H plus concentration, times our OH minus concentration equals 1 times 10 to the minus 14. Here, we're going to solve for the OH minus. It's really the same calculation no matter which one you got going on. So 1 times 10 to the minus 14 divided by our H plus concentration. Putting in our number there on the bottom, or 1.3. That is going to get us 7.7 times 10 to the minus 15 molar here as our H plus concentration. Any questions on that so far there? Again, when you punching this in, a reminder, 1 exponent button, negative button, 14, divided button, 1.3. So again, that is the proper way to punch it in. Again, no multiplication. Remember that this button is a times 10 part of the number. So that's why we don't have to hit the multiplication button or anything like that. Obviously, in this case, it is hydrochloric acid. So we would assume that it's acidic, and it is because, again, our H plus concentration in this case is larger than our OH minus concentration. So it definitely is acidic like we would expect. Question on that one there. All right, why don't you give another one a go here? We have the H plus concentration, what's the OH minus, and is it acidic, basic, or neutral? So take a moment here, see what you come up with. Make sure calculators still work. Okay, so same deal here. We're given the H plus, so we want to find the OH minus. So again, going to our KW to calculate that. That is going to get us our OH minus going to equal our KW value divided by our H plus concentration, which in this case, 1.2 times 10 to the minus 6. Again, we want to make sure that we are using our exponent button here. And if you do that, you do end up with 8.3 times 10 to the minus 9. If your calculator is not in scientific notation, you ended up with a bunch of zeros. An 8 probably at the end. So that's maybe what you ended up with, again, if your calculator was not in scientific notation. So that definitely eliminates these two guys. So now what we need to determine is, is it acidic or basic? By the way, this is a concentration, so we would need molarity written there next to it, or the big M. So at this point, we need to compare the concentration of H plus given to us and our calculated concentration of OH minus. And when you do that correctly, you will see the H plus concentration is actually larger than the OH minus concentration. And that would mean that number 4 here would be correct, as it would be acidic. Questions on that? Now, it's a very common question that sometimes people ask is, wait a second, isn't 9 a bigger number than 6? And yes, it is. 9 is a bigger number than 6. But the other important part of that number is the negative part. So negative 6 means that we're going to go basically 6 places this way and put zeros. Negative 9 means we're going to actually go 9 places this way and put a bunch of zeros like I just did here. And in comparison of those numbers, actually, again, the H plus concentration is larger. So when you're dealing with negative exponents and you're comparing them, the smaller negative exponent is actually the larger number because you're putting less zeros in front of it. Any questions on that? Questions on, and again, if you wrote out this guy, it'd be something like, so you're basically comparing these numbers here. So the comparison of these, this is a bigger number than obviously this guy is at that point. Why did we get rid of answers number 1 and 2? We got rid of answers number 1 and 2 because that value for OH minus would have been 1.2 times 10 to the minus 20, which is not. It's actually this here is our OH minus concentration. So these two right automatically were able to eliminate because it didn't have the right value for OH minus. Other questions on that? Okay. So yeah, so at this point, that's also a very common thing that sometimes people, just naturally think about it like, hey, 9 is larger than 6, so that should be the bigger number. But again, that negative is important because it really does add a bunch of zeros at the back end or the front end of it, making it a smaller number. Any questions on KW or how to calculate it? Okay, so this is a good way to figure out, is something acidic, basic, or neutral. But there's also another very common way, obviously, that we do that, and that is the pH scale. So the pH scale is a measure of acidity. It's really a measure of the H plus concentration that is in the solution. And the pH scale runs from 0 to 7 to like 14 there. And below 7 to 0 is acidic. Above 7 to 14 is basic. And really dead on 7 is neutral. 7 is sort of your center point, if you will. And as you go closer to 0 or in that direction, you're becoming more acidic. As you go from 7 closer to 14, you're becoming more basic. How do we calculate the pH? It is this formula here. The pH is equal to minus the log of the H plus. Again, this is another formula where you might see it minus the log of H3O plus. Again, same thing. Let's talk about calculators and how to punch it in here. First off, if you have a display calculator, you should punch it in your calculator exactly how the formula is. You should hit the negative button, not the subtract button. The negative button, the log button, and you put in your number there in scientific notation using your exponent button. If you have a non-display calculator, this equation and everything else, you need to kind of go backwards, which means you need to punch the number in first, then hit log, then hit the negative button. If you're not sure if you have a display calculator or a non-display calculator, very simple way to do that is to simply hit the log button. And if it says log, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. So again, non-display backwards in terms of these formulas, how you punch in your calculator. Display calculator, just exactly how they're punched in there. Now, an important relationship between H plus and OH minus is this. As the H plus goes up, OH minus goes down, and vice versa. As the H plus goes down, OH minus goes up. So there's sort of that opposite relationship between the concentration of the H plus and OH minus in that solution. And that's going to get us either a pH that is 7 if they're equal to each other. And that's why technically it is neutral at 7, because at that exact point, the concentration is 1 times 10 to the minus 7, which would give you a pH of 7. If you have a larger H plus concentration, you will have a lower pH. And if you have a larger OH minus concentration, you will have a higher pH in that case. So the pH goes up as the H plus goes down, and the OH minus concentration goes up, and vice versa. pH will go down as the H plus concentration goes up and the OH minus concentration goes down in that case. Any questions on that? Let us talk about pH and everybody's favorite thing, which is significant figures. So when you calculate the pH, your answer should have the same number of decimal places as the number of significant figures in the concentration value, and vice versa. So what that means is if the concentration value had one significant figure, you should have one decimal point in your pH. If you had two decimal points in your pH and you're going backwards to the concentration, it should have two significant figures. So that is sort of how we handle sort of decimal places and stuff like that in terms of pH. Why don't we try one real quick here just to make sure everybody's calculator works. Let's say we had an H plus concentration of, we'll go with 1.2 times 10 to the minus 5. So calculate the pH to the proper number of digits there. So if you punch it in, again, pH would equal minus the log 1.2 times 10 to the minus 5. You should get on your calculator 4.920818754. Clearly, that is way too many decimal places there to give in an answer, although I have seen people give that many decimal places. Don't do that, please. So where should we end this? And the rule is, now that we sort of have a couple of numbers to look at, the number of significant figures in our concentration. Our concentration here has two significant figures. That is not how many significant figures we should have in our pH, but it is how many decimal places. So we should actually go to two decimal places in this case. And our answer really should be here 4.92. Two decimal places for the two significant figures in the concentration. And by the way, this would be acidic. Question on that there. And we're going to talk about how to go the other way from like here back to here. And you would follow that same rule. And we would look at that pH value and go, oh, okay, it has two decimal places. So when I write my concentration, I should have two significant figures. Any questions on that there? Okay. Now, there is also a similar scale to pH, but it actually measures something else, which is known as pOH. And the name actually tells you what it is. pOH measures the free OH minus concentration in the solution. And the nice thing about pH and pOH is if you add them together, they will equal 14. So if we add our other stuff into here, pH is equal to minus the log of the H plus. So what does this do? Well, it gives you some options in terms of how you could solve these problems. If we even put in our other guy we saw earlier, our KW, you know, you have a few different options as to how you could kind of approach some of these problems. In addition, why we have sort of all these equations here on the page, let's talk about two other calculations that are done that are also important. And is what I was just talking about. If you have the pH, from the pH, you could get the H plus concentration from that. And you take the inverse log of the minus pH to do that. On your calculator, most calculators, when you hit inverse log, which is basically the top left corner there, the shift button, the second button, and log, that is what pops up a 10 and a caret. This is also why it's very important to be using your exponent button, because a lot of you might be using that version or that way to put in a number in scientific notation. You're going to be messed up in terms of your calculation. So when you hit the inverse log, it typically pops up a 10 and a caret. You want to make sure you do it negative, not subtract button, pH, and that will give you the H plus concentration. In addition, if you have the POH, you could get the OH minus concentration by pretty much the same calculation. The OH minus concentration would equal the inverse log of the minus POH, and that is 10 to the minus basically POH in that case. So all these equations here give you sort of a variety of ways you could sort of answer questions. You might not even have to use KW in certain problems. You could use KW and maybe not do the inverse log, so there's a multitude of ways you could solve some of these problems depending on sort of what is given to you. Any questions on those formulas there? We're going to use some of them here in just a second, obviously. Okay, so on the left here is the pH scale. And again, you can see up there towards the top, we have some sodium hydroxide, which is a strong base, and some strong acid there as well. We have pure water over here, which is 7. Some vinegar, lemon juice, some acids, a lot of household cleaners like we talked about, basic. By the way, if you take some water out of the tap, will it be his pH is 7? It might not be. It might actually be pretty acidic. It might be an acidic in terms of a pH of 5 or something like that. And that's because the water, especially water has been sitting out a while. Water that's been sitting out a while will pick up some CO2 plus some water, make some carbonic acid, increasing the H plus concentration, decreasing the pH. So, if you measure water, sometimes surprises people. If it's not pure water or filtered water really good, it's been sitting out a while, the pH is like in this range. And that's because this process is happening. It's increasing the amount of H plus in that particular solution. Now, a couple important things here before we sort of jump into some calculations is these two guys here. When you are asked, is the solution acidic, basic, or neutral? There is only one answer to that. That solution is either acidic, basic, or neutral. The solution cannot be acidic and basic at the same time, which I've seen people sort of give that answer. And they do that because they're asked to calculate the pH and the POH, and they go, oh, the pH is above 7, it's basic. The POH is below 7, it's acidic, and they give acidic and basic. I don't think I've ever had anybody give all three, which I guess is good, but I definitely have people give both answers. So I personally would recommend that you always look at the pH value when determining is it acidic, basic, or neutral, because for the most part, that is the scale everybody has in their head, is the pH scale. The POH scale actually runs opposite of the pH scale. What I mean by that is it goes to like 14, but from 0 to 7, it's basic. And from 7 to 14, it's acidic. And that's usually not the scale people have in their head. People usually have in their head the one we just talked about, which is on this page here, that below 7 is acidic and above 7 is basic. So always, 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 I would recommend look at the pH value when you're trying to determine, acidic, basic, or neutral. Make sure you don't do it off of the POH value, because you'll probably get it wrong and because you'll have a backwards number. Any questions on that there? All right, so let's try some calculations here and see what we got going on. We got a couple here. Top one is the rainwater is collected and the pH is 4.82. What is the H plus? Why don't we just do a whole bunch just to make sure all of our calculations work here. Our calculator is working. Let's also calculate the OH minus concentration. Let's calculate the POH on that first one as well. Obviously the H plus concentration. And then let's also figure out, is it acidic, basic, or neutral? On the second one, we have an OH minus concentration of given. What is the pH? So let's also do, in addition to the pH, let's do the POH. Let's do the H plus concentration, and let's determine, is it acidic, basic, or neutral? All right, so take a few minutes here for each of them and figure out those things, make sure our calculators work and all that good stuff. So since we're really kind of looking for everything here, you do have a couple of different places where obviously you can start. So in the first one, they gave us the pH. So we could just answer the first part of the question. We could take the pH and remember that if you have the pH, the H plus concentration will equal the inverse log of the minus pH. So again, on your calculator, you basically hit that second button on the top left or the shift button. And again, it usually will pop up a 10 and a caret on most people's calculators. You want to make sure that you do a minus, not minus like subtract, but a negative 4.82. And if you do that, it looks like you will end up with 1.5 to the minus 5. Again, this is a concentration, so it should have a unit associated with it there. First off, any questions on that calculation? The other thing that we could get kind of right off that as well is that we could get the POH. So remember that the pH plus the POH equals 14. That would mean that the POH would equal 14 minus 4.82. And that would get me 9.18 as my POH. Now that I have my POH, I can use it to get my OH minus by doing the same calculation as with the H plus. And that would be the inverse log of the minus POH. And that's going to give me 10 and a caret minus 9.18. And that would get me, looks like maybe 6.6 to the minus 10. Also going to need some units here because it is a concentration. By the way, you could have, if you wanted to, also use kW here with that value since we already figured it out, and you obviously should end up with pretty much the exact same answer as well. So again, there's a few different ways you could kind of get to some of these answers depending on sort of the approach that you take. That's that. That leaves us, is it acidic, basic, or neutral? So again here, we're going to look at the pH value, not the POH value. And the pH value is 4.82, which means it is acidic. And only acidic, not basic as well. Any questions on any of the parts of those calculations there? Also, a couple of things when we looked at our pH value originally, had 2 decimal places. That is why we got 2 significant figures here in our concentration values as well. So again, that basically, as we talked about earlier, works both ways. Any questions on any part of that first one there? All right, so if we look at the second one there, kind of taking the same approach, we have the OH minus. So you really do have a couple of options in this case. You could go into KW and get the H plus if you wanted to, and then got the pH that way. In this particular case, what I'm going to do is actually calculate the POH first, which is minus the log of our OH minus, which in this case is minus the log of 2.5 times 10 to the minus 7. Gets us 6.60 as our POH. Now that I have the POH, I could use the pH plus the POH is equal to 14 to get my pH, which basically is 14 minus the POH. And that would get me 7.40 for our pH. And again, at this point, since I have the pH, I could do the inverse log of it. Since I also have obviously that, I could do KW. So I'll do KW in this one. And again, it should kind of come out the same. Maybe slightly off with some rounding, but you know, it will pretty much end up the same answer at the end there. Just actually write the right formula there. That's H plus times OH minus is equal to 1 times 10 to the minus 14. So our H plus in this case should be 1 times 10 to the minus 14 divided by 2.5 times 10 to the minus 7. And that would get us about 4.0 times 10 to the minus 8, I believe. Also, again, needs some units as it is a concentration. Any questions on any of those calculations there? Oh, by the way, we need to determine, is it acidic, basic, or neutral here? It is actually going to be based off of the pH value here. 7.4 is above 7. It is basic, slightly basic, but it's basic. Again, remember, we will make it simple in this class for us. It's 7 on the nose. It's neutral. If it's not 7, then it's either slightly acidic or slightly basic. That's a good way to do it. You know, it's not very basic or very acidic in that sort of 7-ish range, but we'll go with, just to make it pretty clear, it needs to be a pH of 7 to be neutral. Otherwise, again, it's slightly one way or the other, basically. Questions on that? Okay. So I'm going to try another one here, kind of the same stuff. We're looking for pretty much all the same stuff there, but we're starting with an H plus concentration of 3.5 times 10 to the minus 6. So take a moment or two here and see what you come up with. Yeah, so on this one, we're given the H plus concentration, so it's a good place to start. We'll go right into the pH. So the pH is minus the log of the H plus. That's going to be minus the log of 3.5 times 10 to the minus 6. And that's going to get us a pH of 5.46 in this particular case. Once I have the pH, the POH is very easily found by, again, taking that relationship. So the POH would basically be 14 minus our 5.46, and that's going to get us 854 as our POH. And we want also the OH minus concentration. So, you know, again, there's couple different ways you could do that, but we'll go with the OH minus is equal to the inverse log of the minus POH. In your calculator, again, when you do that, should look probably something like this. And if we do that, looks like maybe a 2.9 to the minus 9. And again, we do need a unit here as it is a concentration. And I think that was everything it asked for, except we'll add in, it is going to be based off of obviously the pH value here, acidic as well. Question on any of those calculations, how to calculate H plus, OH minus, pH, POH. Obviously, you need to be able to do all of those things. And again, remember, only one answer in terms of acidic, basic, or neutral. Don't list them all. Any questions on that? Okay, so then let us continue here. And let's talk a little about some differences in terms of some acids and bases that we see. First off, an electrolyte, just a reminder, is you might remember electrolytes. Electrolytes are really things that break apart into solution. They produce ions, right? So electrolytes are really guys that really produce ions in solution. Ions in solution, like these guys here, basically allow it to conduct electricity really well. So this is usually accompanied by a demonstration of a light bulb. Strong electrolyte, because it 100% breaks apart into its ions, produces a lot of ions, good conductor electricity, light bulb, very bright. There's also weak electrolytes, which do break apart into ions, like acetic acid here. But in solution, they are mainly stay together. So in solution, they mainly stay together. But because they're able to still produce a few ions, they're considered an electrolyte, but they're considered a weak electrolyte. And in sort of the example of the light bulb, unlike up here, where light bulb would be very, very bright, light bulb here will be very dim. It will still go off, but it'll be very, very dim. So what about strong electrolytes? Well, strong electrolytes are strong acids, or vice versa. Strong acids are strong electrolytes. And what does that mean? It means they 100% break apart into ions. You have absolutely none of the strong acids still together in that solution when it's floating around. These are all basically strong acids that are dissociating in water. Here they do include water in the reaction, and that's why we do produce H3O plus on each of these. Each of these reactions could just be simplified by writing this reaction. And again, without the water, we get the H plus. So again, it's just a more simplified version of the same reaction. What's basically happening here is we have this acid in solution. And when we have an acid in solution like hydrochloric acid, it is 100% the H plus and Cl minuses floating around. You have absolutely none of the HCl units still together when it goes for a swim because it's a strong electrolyte. Any questions on that? That's why it really is considered a strong acid, because it pretty much just needs to go for a swim, and it produces a lot of free H plus very quickly, and thus why it is considered, like I said before, a strong acid. These are some really strong acids: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid is a strong acid, hydriodic acid is a strong acid. So these 6 here are some very strong acids that we come across a lot. So you should keep those kind of in mind. Weak acids, on the other hand, are reversible reactions. So we have those arrows that are heading in the opposite directions here. And they're basically weak electrolytes. And what that means is, again, in the case of, say, HF, it is mainly going to stay together. So in solution, you would mainly have HF guys floating around, but you'll produce a few of these kind of ions floating around in the solution. But the main one that's there are these HF units are still there. So since it's able to still produce some ions in solution, it's still an electrolyte. It's still an acid because it can produce some H plus that's free in solution as well. But it's a much weaker acid than, say, hydrochloric acid, which 100% breaks apart. So because this guy mainly stays together, it doesn't produce as much free H plus or H3O plus, making it a weaker acid than hydrochloric acid. These also have basically the water involved. You could simplify these equations just like the others by taking the water out, and what you would be left with is just the H plus and F minus. So again, this is also an acceptable way of representing these equations. Either way is perfectly fine. And again, most of the time, I probably will be doing that way of it, and it does represent the same thing. questions on that there? Strong bases, just like strong acids, are strong electrolytes. They also 100% break apart. And that essentially means that they will 100% in solution have these guys floating around. That means we make a lot of OH minus, and that's why it is a strong base. So in solution, if you throw some sodium hydroxide in there, this is pretty much what you got going on. You have none of the NaOH units still together. And again, just by it going for a swim there is going to produce a lot of free OH minus in that solution. Again, remembering that the greater the OH minus concentration, the smaller the H plus concentration, and the higher the pH is. And again, that's why it's considered a strong base. The ability to produce a lot of OH minus sort of very quickly, if you will, in solution. Any questions on that there? And just like weak acids, we do have some weak bases. And our weak bases also are these reversible reactions. And just like our weak acids, they pretty much stay together, but are able to produce a little bit of these ions in solution. And again, because they're able to produce a little bit of the OH minus, they're obviously still considered a base, but they will not produce anywhere near the amount a strong base would when it goes for a swim. Now, there's an important sort of relationship between an acid and its conjugate base pair and a base and its conjugate acid pair. And it's sort of an opposite relationship. So what that means is if you have an acid and its conjugate base pair partner on the other side of the arrow, basically, if this acid is a strong acid, its partner will be relatively weak. And what we mean by that is, we'll talk a little bit more about it later in this chapter, but what it basically means is the conjugate base will really not continue to react. It won't react with water or anything like that and kind of mess up the pH. If it's a weak acid, its conjugate base partner is going to be relatively strong. And as we'll see later in this chapter, that means it is going to continue to react and cause a little bit of an effect on the pH as well. So there's sort of an opposite relationship between these things. Same thing holds true for the base and its conjugate acid. If it's a strong base, its conjugate acid will be relatively weak. If it is a weak base from which the conjugate acid comes from, it will be relatively strong. So there's sort of, again, that sort of opposite relationship, which is important, especially when we start talking about salts and hydrolysis. That sort of opposite relation, a really important thing to understand. Any questions on that? In solution, H3O plus and OH minus are really sort of the strongest acid and bases that can exist when we look at them. Here's a table. You have similar ones in your book, but it does list sort of that relationship that we see, strong acids up here. These are a lot of strong acids, or perchloric acid, or HI, HBr, HCl, HNO3. These are a lot of these guys. Opposite side are, because they're strong, these guys over here, their partners are relatively weak. So they really don't react with water is really what we're going to be talking about in that sort of effect. On the bottom here, we got kind of weaker acids, and their relative partners are going to be stronger on this side. So again, it's that opposite relationship. These guys were the ones we talked about in terms of recognizing these guys as strong acids. How would you recognize some of these other ones as weak acids? We'll talk about that in this chapter as well, but there's a lot of clues that could really help you determine if something is going to be weak or strong or not. And here's just a picture of that, kind of like what I was drawing in our strong acid. You can see pretty much in solution, 100% of what you have floating around is the ions, none of the whole guide together. And that's opposite here in a weak acid. Pretty much when it's all done, you pretty much have the whole thing still together, a little bit of ions. Here, 100% ions, none of this guy left. So it all pretty much breaks apart. This is important because up until now, we've had problems where they give you the H plus concentration, the OH minus concentration, but sometimes you may be given an actual formula and you need to kind of be able to recognize it as a strong acid or a strong base and be able to calculate the pH of it, perhaps. So what happens if we do have that? So why don't you give it a try? I'll give you a hint. Both of these guys are strong. Well, one's a strong acid and one's a strong base. So take a couple of minutes here and see if you can figure out what the pH should be for each of these guys. So take a moment here, treating these guys as a strong acid in the first one, and obviously a strong base in the second one. So try to figure out what you need to calculate the pH, try to figure out how to get it, and we'll talk about it here in a couple of minutes. Basically in solution, it is not going to stay together. It is 100% going to break apart into H plus ions and NO3 minus ions. And what's important here in terms of the pH? Well, the pH is minus the log of the H plus, which means I really need to figure out, what I got going on here. So what we know is because this is a strong acid, it's going to break apart into these guys. So what we need is really the concentration of these ions in solution. So if you remember when we talked about concentrations, you could kind of do it like stoichiometry. It's a 1-to-1 relationship here, which means the concentration of the H plus should be 2 times 10 to the minus 3. By the way, it's a 1-to-1 relationship for this guy as well, although we don't really need him in this problem. We only really need this because that is now going to be the H plus concentration, which means we can now go into our pH, and that would give us 2 times 10 to the minus 3, and that would get us a 2.7 pH in this particular case. Questions on that calculation? It is 1 sig fig here. It is 1 decimal place here. So that's why, again, we went to only 1 decimal place in that particular case. So when you're given, say, a formula of a strong acid and you're asked to calculate the pH, you really just need to figure out, what is the H plus concentration? And if it's basically a monoprotic acid, which means it has 1 H to give, it's probably going to be the same concentration, both of these guys. So, you want to kind of figure out that H plus concentration, and that allows you to get to the pH. Now we have barium hydroxide, which is a strong base. So just like our nitric acid, when it goes for a swim, it's going to 100% break apart into a barium ion and actually 2 hydroxide ions here. As this guy will come to the front, there's basically 2 of them. Now, what's important for the pH here is actually the OH minus concentration, because that's going to allow us not to get to the pH directly, but it's going to allow us to get to the POH and then to the pH. So that will allow us this sort of route to get to the pH from here. So we kind of take the same approach. This is 1.8 times 10 to the minus 2. It is, though, in this case, a 1-to-2 relationship here between the whole thing and just the hydroxide, which means you actually do need to multiply the concentration by 2 to get the proper concentration for hydroxide in that solution, because there's basically twice as much hydroxide floating around. And that gets you a 3.6 to the minus 2. That's going to allow us to go into our POH, which would be minus the log of 3.6 times 10 to the minus 2. Going to give us a 1.44 on our POH. We then can use our pH is 14 minus the POH, and that will give us 14 minus 1.44. Which, by the way, if you, got the 1.44 and you thought that was the answer, it really shouldn't make sense to you, because it's a base, right? So 144 would not be the right pH. So if we do that, it looks like maybe a 12.56 on the pH, which should make sense to you because it is basic, and this is obviously a base, so that does definitely make sense. Any questions on this type of calculation? So again, you may be given, you know, something that's not sort of generic like H plus OH minus, maybe given a formula, and if you could recognize it as a strong acid, you pretty much need to calculate what the H plus concentration is. And if you could recognize it as a strong base, you need to get the OH minus concentration that allow you to get to the OH and then the POH. Any questions on that? Okay, that is probably a good place to stop here lecturing right at this moment.